Look, you can't put negative numbers inside a logarithm. So for an example, let's not do natural log. Let's do common log. Everyone's favorite log. What power do you raise 10 to make it equal to negative 10? You know, what number do you put up here to make it equal to negative 10? You can't do it, right? Exponents don't change the sign of a number. You could put in negative 1,000, but negative 1,000 actually doesn't change the sign. It just means it's 1 over 10 to the 1,000th power. That's 10 to the negative 1,000th. Okay? So you can't put a negative number inside a logarithm. That's important for this one. We have to make sure that 3 minus x is greater than 0. So that's how we're going to determine the domain. Okay? So to solve that, we can add x to both sides, and then we're done. You can flip that around, make sure it's just pointing the same way. X is less than 3. That's our domain. In interval notation, negative infinity is as small as we can go. 3 is as big as we can go. And a parentheses because it doesn't have the line underneath. So there's the domain. The range is a different story, but to know the range, you just need to know how logarithms behave. Log of x looks like this on a graph. Starts really low, just slightly to the right of x equals 0 because we can't have x equals 0, and I'll show you why in just a second. And it never stops climbing. So the range of this graph is going to be, the range is negative infinity to infinity. Okay? Because if, yeah, it doesn't matter if it was multiplied by negative or not. So that's our domain, that's our range. And so with this one, I drew it approaching 0 but never touching it. Because you can't put a negative number in a log, but think about what log of 0 means. Log of 0 means what power do you raise 10 to be? You know, put a number in the exponent to make it equal to 0. Can you ever do that? You could plug in like negative 1,000 or negative 10,000 or negative 100,000, but that's never going to exactly equal 0. So you can't put in 0 in a logarithm either. That's why in this inequality I didn't write the greater than or equal to symbol there. Okay, can't put in 0, so that means 3 is our vertical asymptote. So draw the graph. At x equals 3, we're going to have a vertical asymptote. But since this is a negative x, we'll want to think about the behavior of the graph. We'll change that in just a second. Probably getting some points would be a good idea. Look, for all logarithms, log of 1 is 0. Because what power do you raise 10 to be to make it equal 1? 10 to the 0 power is 1, right? So in this graph, quick x and y chart, if we plug in x equals 2, we get out 0 here for the same reason I just explained over here. Because 3 minus 2 is 1. Natural log of 0 is 1. Is 0. Sorry, natural log of 0 is 0. I said that incorrectly. Okay, that's 0. 0 times 2 is 0. 0 minus 4 is negative 4. So we know we're supposed to have a dot at 2, comma, negative 4. Now, if we're supposed to have a vertical asymptote right here at x equals 3, but a dot over there, then that must mean that the graph looks different than this graph over here. Okay, and what you're actually going to see if you get another data point, like negative 7, if you plug in negative 7, then 3 minus negative 7 is 10. Oh, wait, we want e. Okay, that's a little bit more challenging. But the big idea is that since this is supposed to be a vertical asymptote, since we have a dot over here, the negative sign has changed the behavior so that the graph should look like this. And then the minus 4 doesn't really impact things that much because it's going to infinity. The times 2 doesn't either. You just change it so that it would rise at a faster rate. But you're all pretty good with graphing calculators. You can punch that in a graphing calculator too.